Welcome back to your course on Introduction to Data Structures and Algorithms. The topic for today's discussion is time and space complexities and asymptotic notations. Before moving on to time and space complexities and what they are, let us discuss why do we need it. When we're studying algorithms, we come across a term known as performance, referring to performance of an algorithm, right? Now, if we are to describe performance of an algorithm, it can be described as the efficiency of the algorithm on a particular machine with n number of inputs, right? So performance analysis is basically understanding how an algorithm performs when it is made to run on a certain platform and it is given certain n inputs. So there are also other things that should be taken care of, like the software that you design should be user friendly, easy to use, and it should have a good security features and maintenance features, etc. But there is one major concern, that is about performance. So performance can also directly be related to speed, right? Performance, say, is directly proportional to the speed, obviously, of computation, right? So when we are measuring performance, our main criteria is measuring the speed of that algorithm. And second can be correctness of algorithm. Say that your algorithm is extremely fast, but it does not work as per our requirement and gives incorrect inputs for some n inputs and correct outputs for some n inputs, which is wrong. So performance is firstly directly proportional to the speed of computation, and second to the correctness of our algorithm, right? So now say if we are given two algorithms, right? We have two algorithms with us, say A and B. I have given them names as A and B. How do we find out which one is better, right? Fine. Which one is better? You can pause the video and take a minute to think about how will you find out whether the algorithm A is better or B is better. So I think your approach will firstly be run the two algorithms. Run both and check, right? Now, with this approach, there can be problems like difference of input. Say for some set of input, A works faster, but for the other set of inputs, B works faster. So that will give you a, a biased answer to it, which one is better, right? Second is that it is it can be machine independent, that is hard machine dependent, that is the hardware you use, the processor that is engaged, or even the programming language. Say for example, C is faster than C++. So if your program is written in C language, it will execute faster. So if you actually run both and check on your system, it is not a correct approach to decide which of the two algorithms is best. Firstly, because of difference in input, that for different input you might receive a different output for both cases. And secondly, the fact that dependent, that would be hardware plus programming language. Right? So this is not the best approach to finding out which out of the two algorithms is best. So what we do, what is time and space complexity, right? So the complexity of an algorithm is a describing the efficiency function describing the efficiency of an algorithm in terms of the amount of data the algorithm must process, right? So there are two types of complexities: time complexity and space complexity. Time complexity is a function that describes the amount of time taken, right? And that is in terms of not when you actually run it and find out the time in milliseconds, but it is in terms of the amount of input to the algorithm. Similarly, space complexity is a function describing the amount of memory or space an algorithm takes, that too in terms of the amount of input given to the algorithm, right? So coming to again, why do we need complexity analysis? We have seen that to compare between two algorithms, we cannot take the approach to run and check in our system, and so we need a complexity analysis, right? So for this matter, let us consider an example. Say that you have to write a program to find out the sum of first n even numbers, right? There are two programmers, A and B. There are two different sum functions to calculate the same even sum int n, which returns n into n plus 1, and uh, even sum int n, he defines the current value to be 2 and sum will be equal to 0. Then he runs the loop for int I equal to 1, I less than n, I plus plus, then sum equal to sum plus current value. So each time 2 will be incremented, and then the sum will be calculated for all even numbers. So these are uh, two approaches for the same program. And now we need to analyze which out of these two is a better approach. Here is where the use of complexity analysis actually comes. So, if we talk about this particular function, we see that the function is called, n is inputted, which is the number up to which we have to find the sum of the even numbers. So, say that you input 2 here, so the output should be 2 plus 4, which is the two even numbers. So that would be 6, right? So this should be the output. This contains one statement that returns simply the output. So we see here that it is a constant value. That is, it is not in fact actually dependent upon the number of times you call the function. It is a constant function. So let us write it as C1, right? Talking about this function, int even sum int n, you initialize the variables current and 0 equal to 2 and 0 respectively, and then you run a loop for int I equal to 1, I is less than equal to n, I plus plus. So both of these statements which are present within the for loop will run for these n times, right? And here you return the sum. So since uh, these two statements are running for n times, the complexity of the program will increase, right? So let us write here, this is again constant, this is also constant. So we will write another constant, plus it will have a C3n because the for loop executes for n times. Now that we do compare the complexity of A, right? complexities A and B. This is a constant complexity, but this depends upon n. So this is n and this is a constant complexity. So when we compare all of this is a better algorithm because it is not dependent upon the value of n, right? However, this is dependent on n. Now, if let us say we have another third algorithm, hypothetically, which has two for loops, right? So it has this for loop, and within it there is another for loop, right? With certain statements. So now the statements will execute for n square times. So we can write the complexity of C as C4 plus T5n plus C6n square, right? For C, we will write it as C4 plus C5n plus C6n square. Now, n square is a further higher complexity. So, this will be the worst out of all three. This will have an average, and this will be the best one out of all three because it is not dependent upon n. This is dependent upon n as it is directly proportional, and this is exponentially dependent upon n, say n square times. So I hope why do we need complexity analysis is clear, and how do we actually find out complexity for a given program is also clear with this example. Now we come to another approach, another term of a function which is known as order of growth. Now order of growth is the same as what we've discussed in the previous slide. It is the basis of comparison of two algorithms, right? So considering the same example as we took in the last, we received the complexity of A to be C1, complexity of B to be C2 plus C3n, and complexity of C, as we hypothetically took it, to be C4 plus C5n plus C6n square, right? So this was the complexity. Now to find out the direct method for order of growth will be 1 in this case because it is constant, not dependent upon n. To find order of growth for this, firstly, this is the first step, this is the second step. First step says that ignore the lower order terms. Lower order terms meaning those with lower value of n. Now here n to the power 1 is the highest power, so we will ignore C2. Second step to it is ignore the leading constant. Leading constant meaning the constant with n. So order of growth of this function, particular function, is n simply. Applying the same method to the third, we ignore the lower order terms, that is C4 also, C5n also, because here the highest one is n square. And then we ignore the leading constant, which is C6. So order of growth of this hypothetical third algorithm, or the algorithm named C, is n square. So this is what order of growth is. Order of growth is simply the rate of changes of an algorithm with respect to the input, right? So this is our direct method which we usually follow. In fact, in certain competitive exams also, there are questions where you are given an algorithm, say for this example, and you're supposed to find out the complexity or order of growth for the particular algorithm. So the procedure that you will follow will have the same. First, you will write the function that you derive out of that program, and then you follow this direct method. You ignore the lower order terms, you ignore the leading constant, and what you get as a result will be the order of growth, right? Now, there are certain terms known as worst, average, and best case complexities. And we also have a term called asymptotic analysis. Now, what is that? Worst, average, and best case, they are forms of complexities, right? And why are these? For us, any algorithm in this world, you consider any algorithm, there will be a certain best case for it, an average case for it, and a worst case for it, right? So, for an example, let us consider that you are a class of 40 students, right? And your names are ordered alphabetically in a given register from A to Z. You are supposed to find out the roll number of a student named Akash. Now, since it starts with N, it will be present within the first few. Probably it is the first roll number of the class. So, for you, finding out Akash as the first roll number will be the best case scenario because it is located at the first position itself, right? Now, if you are supposed to find out a person named Kabir, right? So that will somewhere be in between. Not the best case, but not the worst case either. So you will have to traverse through the register until you find Kabir, and it will not include all cases, but definitely, yes, some of the cases. So this will have an average case complexity. Now, if your name is Zeal, right, you will have to traverse all the way from name starting A to the name starting Z to finally find out Zeal, which is probably the last roll number of the class. So that will be a worst case complexity. Why? Because your uh, object that you had to search for was located at the last, and you had to go through all of the above inputs to it. So that will be a worst case complexity. Now, when you actually analyze algorithms, what you consider is the worst case complexity, because obviously best case doesn't really work in the ideal world. Average case is just fine, but when you know what the worst is, you can assure the customer that suppose in the worst case, if your program performs in say 10 milliseconds, that is your efficiency. In best case it might perform in 1 millisecond, but it is not important because all the cases there will not be executed in 1 millisecond. So if you tell the user of your program that in the worst case your program shall perform in 10 milliseconds, so he will be assured that best or worst, the maximum time taken by my program will be 10 milliseconds. So that is the reason why when we actually calculate complexities, we consider only the worst case complexity majorly, and the best and average cases are just for mere knowledge. Now, what is asymptotic analysis? Asymptotic analysis is just a name given to evaluating the performance of an algorithm in terms input size, right? And considering this input size only, we just discussed worst, average, and best cases, right? So we calculate how the time or space taken by an algorithm increases with respect to the input size given to it, right? And why do we consider asymptotic analysis? Because as we discussed the first approach here, which was actually running both algorithms and checking, it is not as efficient because of difference of input and the fact that it is machine dependent. If we use asymptotic analysis, that is calculating the performance in terms of input size, it is definitely not the perfect way, but it is by far the best way available for analyzing algorithms, right? So with asymptotic analysis, we can't judge which one is better because we ignore the constants, right? While finding the complexity, we ignore constants. But uh, we cannot exactly measure like numerically which one is better, but we always talk about input sizes which are larger than a particular constant value, right? So it is by far the best way to check which algorithm will be better, and you can analyze very efficiently that which of the algorithms available will be the best in which case, and you may end up choosing an algorithm which is uh, efficient as well as fast for your system. So now the time required by an algorithm falls under three types as we've discussed: best, average, and worst cases. Best case will be the minimum time required for a program execution. Like here we discussed finding out Akash from a registry of students from A to Z, because Akash will be present at the very first roll number, right? Similarly, average case will be the average time required for a program execution. In this case, we find it out like find the name Kabir from this list will be an average case complexity, and worst case will be the maximum time required for the program execution. It will be finding out zeal because it will be located at the last roll number. Now, in terms of asymptotic analysis, there are certain notations known as asymptotic notations. So, for the worst case, there is a big O notation. For average case, there is a theta notation. And for best case, what we use is an omega notation. So, let us like understand all of these three notations in detail. So, big O notation, firstly, which denotes as the upper bound of an algorithm, meaning that it bounds the function from above, the worst case, right? Now, mathematically speaking, the big O notation of a function can be defined as a function g of n if there exists constant c greater than 0 and n greater than 0, such that f of n is less than equal to c g of n for all n greater than n naught, right? Similarly, the little o is used to describe an upper bound that cannot be typed, that is just a loose upper bound. To understand this, let us consider a function, say 2n plus 4. This is the function that we have. Now, our function f of n, this is our f of n, right? So, considering the function equal to f of n equal to 2n plus 4, we need to find constants such that c greater than 0 and n greater than 0, such that f of n is less than equal to c g of n for all n greater than 0. Now, g of n here is the order of growth function, right? So, in this case, following the direct method of finding the order of growth, we ignore the constant term and we ignore the uh, leading coefficient. So, order of growth here is n. So, replacing the value of f of n and c of n in our given condition, f of n is less than equal to c times g of n, right? F of n is here 2n plus 4 is less than equal to c times g of n, which is n in this case, right? So now for the matter of C here, when we are finding the big O notation and finding the solution for our big O function, what we do is that we take the constant as 1 plus the coefficient of the highest term. So in this case, the coefficient of our highest term is 2. So C is taken as 1 plus the coefficient of highest term, which is 3. Right? So replacing the value of 3 in the function, 2n plus 4 is less than equal to 3n. So n must be greater than equal to 4, right? So n must be greater than equal to 4. So in this case, our n naught is 4. So we have found that constant c, which is greater than 0, and our value that we found is 3, and n, which is greater than 0, which is equal to 4. So for this function, the complexity is big O of n, which is our answer. Moving on to omega notation or lower bound, it measures the best case time complexity, or the best amount of time an algorithm can possibly take to complete. Mathematically, omega of f of n greater than equal to g of n is such that there exists constant c greater than 0 and n naught greater than 0, such that g of n is less than equal to c times f of n for all n greater than equal to 0. So taking the function again, f of n as 2n plus 4, and g of n again as n, which is the order of growth function, we take n less than equal to c times 2n plus 4. Now if we are finding the lower bound, the constant that we take will be the leading coefficient minus 1. So in this case, it will be 2 minus 1, which is 1. So n should be less than equal to 2n plus 4, right? Minus n less than equal to 4. So n should be less than equal to minus 4. I'm sorry. This definition here is incorrect. The c has to come here. C times g of n is less than equal to f of n. So replacing the value of c equal to 1 here, it will be 1 times n is less than equal to 2n plus 4. So n is less than equal to 2n plus 4, right? So for any value of n, if we take, n will obviously be less than equal to 2n plus 4, right? So for all values, so n is greater than equal to 0, and c, as we found out, is equal to 1. So the complexity, so we have satisfied the function here, and the lower bound complexity, or the omega notation complexity, will be omega of n in this case. Moving on to the theta notation, which is our exact bound, is the formal way to express both the lower bound and the upper bound of an algorithm. So what it does, it is that it calculates both our lower and upper bounds. So the function is written like c1 g of n less than equal to f of n less than equal to c2 g of n for all n greater than equal to n naught. So what we are supposed to do is find out c1 and c2 and the value of n naught here, right? So again, using the same function 2n plus 4, we found that C1 in case of lower bound was 1 times n, and in case of upper bound it was 3 times n. So we know constant C1 is 1, C2 is 3, and the value of n naught is also 3. Why? Because it is greater than equal to 1, greater than equal to 3. So n will be greater than equal to 0 here, or n will be greater than equal to 3 here. So considering the higher value, n naught will be 3. Since we found two values of n, so it will be greater than equal to 3. So once we find out all this, the complexity in terms of theta notation will be theta of n, right? So these are our notations, and this is how we compare with the function to find out the complexity in terms of big O notation, which is the upper bound, omega notation, which is the lower bound, and theta notation, which is the exact bound. Now, since we've calculated the complexities in terms of all of these notations for the function 2n plus 4, we can conclude that for big O, the best case complexity for any algorithm of this function 2n plus 4 will be big O of n, and same will be the complexities for omega notation and the theta notation. What this concludes is that for any case, best, worst, or average, the performance of our algorithm will be same. And by performance, we are calculating only in terms of input size. So our algorithm, the algorithm we have written for whom the function is 2n plus 4, you give it the best case, the worst case, or the average case, the performance of that algorithm will remain constant. Now there are also certain algorithms for which we have different values for best case and worst case. The example that we've just considered had the same values, but it is not necessary that all functions will perform the same way in terms of best, worst, and average case. Right? So when you actually calculate all of this best, worst, and average case complexity, you get to know that in terms of best case, how will your algorithm perform? And in terms of average case or worst case, how will your algorithm perform? So this is how we analyze our algorithms. Moving on to finally the space complexity. Space complexity is, as we already discussed in the uh, first slide, space complexity is a function describing the amount of memory, not time, amount of memory or space an algorithm takes in terms of the amount of input to the algorithm. So it is similar to time complexity, but the function considered here is our space or memory, right, in terms of algorithm occupancy. Now, when we talk about a space complexity of an algorithm, memory is basically used by variables in an algorithm, by the instructions of a program, like the subsequent instructions that we follow, and finally the execution of our program, right? So these are basically the 3 points where memory is being used. Variables when we actually assign values, instructions which we actually execute within the program. So like if you're assigning a certain memory in between the program, that will be a part of instructions of the program, and execution of the program, that is the memory the program takes when it's finally executing with the actual input. So space complexity will be auxiliary space plus the input space. Input space will be in terms of the variables we assign or the input that we give. And auxiliary space is the space taken by the program when it is under execution, right? So auxiliary space can be defined as the order of growth of extra space, or the temporary space as we can also call it, in terms of input size. And space complexity, we can define it to be order of growth of memory or RAM, right? Space in terms of input size. However, in actual world, we are more concerned with time complexity and not too much in case of space complexity, because today, with the large, good, efficient hardware that we have, space is not much of a concern, but time definitely is. Also, space complexity is quite as much dependent upon the hardware that you are using, the specifications of your device, and not the logic that you are used to implementing in your algorithm. So that is why time complexity is one major concern that is directly related to the logic that you use. However, space complexity is not as much a concern as time complexity is. Thank you.